Hello, can you hear me? Can anyone just
Yes, sir. Good evening, sir.
Okay, good evening. Okay, so I think we should just wait a couple of more minutes so that others can join. Then we'll begin. Till then, one point to be noted is that you should pin my screen or actually make it full screen so that you can see it properly. Okay, we'll wait just a couple of more minutes and then we'll begin. Okay, so I think we should start. Others can join simultaneously. So, good evening, everyone, and I welcome you all for this second live session for the course Introduction to Semiconductor Devices. Today, we are expecting Professor Imani to join also, so hopefully, he will join. So, this course is being taught by Professor N.K. Imani from IIT Hyderabad, and I am your official PMRF TA for conducting these live sessions. I am a PhD scholar at IIT Madras. I work in experimental high energy physics in the CMS experiment at Large Hadron Collider. So that's enough about me, and let's get started. So can anyone just confirm that you can see my screen? I have just changed the slide. Can you see it?
Yes, sir.
Okay, thank you for confirming. Okay, so as you are familiar now, so the plan for these sessions from my side is as follows. So for the first 10 or 15 minutes, I briefly will just discuss the review of the current week's lecture content. That will just give you a brief recap and say a refresher of what was taught in the regular lectures by Professor Imani. Then we'll move on to the actual content of these sessions, that is solving assignment problems, which are primarily from the previous course of offerings. Also, I have included couple of GATE exam course exams questions relevant to the this week's lecture content, so that you can get feel that what you are learning is actually important in these competitive exams. Also, again, needless to say that these sessions are supposed to be interactive sessions, so feel free to stop me at any time and ask me, or you can just comment or give feedback at any time. Just feel free. This is different from your live, different from your regular lecture, so don't feel shy or anything. Okay, so just a moment. Okay, I think I'll just start with the brief review of this week's content. So in this week's, this week actually began with the concept of effective mass, especially in the semiconductors. So what it tells you is that it actually relates the motion of the charged particles, say electron or holes, inside a crystal to an externally applied force. So as Professor Imani also has taught in his lectures, that let's say if you have a crystal, let's say, and you are given a potential, let's say of a 1 volt or anything, and another end is grounded. So the charge carriers inside this particular crystal feels two kind of forces. So the F total, we can say, is the force up due to the applied external potential, so that is F external, as well as there is an internal force due to the presence of lattice inside the crystal, so internal force. So this internal force is quite complex, and so we cannot model it easily. So what we do is we add a concept of effective mass, in which the total force is actually given by m star times the acceleration, where m star is uh, essentially captures the presence of the internal lattice structure and the force given by force experienced by particle while moving through this crystal. So F total is directly proportional to the acceleration with the proportionality constant given as the m star, which is actually the effective mass of charge carriers inside the crystal. So as it is written here that it takes into account the effect of crystal lattice on the motion of the particle. So how do we calculate this? How do we derive the formula for m star? So for this we use the so-called EK relationship. So taking a simple example in which the energy is given as a parabolic function of the wave vector k, so h cross k square by twice m. So if you just differentiate it with respect to k, so we will have dE by dk given by h cross k by m. So by the analogy of P, which is equal to mass times volume, is equal to h cross k, we can say that dE by dk is actually nothing but h cross k, which is momentum, that is mass times volume, mass times velocity, sorry, divided by m here. So what we can say from this is that if you take the double differentiation of this and we'll get the value of m star basically, that is d2e over dk square with h cross square is equal to m star. So this is the concept of effective mass inside the crystal. And okay, so I would like to give you just one small question from this particular expression, that m star is actually sorry, this is 1 over m star. So m star is actually proportional inversely to the second derivative of the energy with respect to the wave vector k. So if I just draw a couple of ek diagrams for ek diagrams, so this is E versus K, and let me take another. One more I'll add, and if I call this as A, B, and C, so can anyone just tell me that which of these curves which of the curves belong to the particles has higher or say that what is the relation of uh, effective mass in these three particular cases? So basically what I'm asking is m star A, m star for B, and m star for C. What is the relation between these three quantities? So one hint you can take from this expression is that the m star is inversely proportional to the curvature. M star is actually inversely proportional to the double derivative, that is essentially the curvature in the EK diagram. So I would like to ask if you can just unmute yourself and tell me what do you think will be the relation?
So M star A is maximum.
Just a minute. Okay, so what are you saying?
So M star A is maximum, then M star B, then M star C.
Okay, so can you just explain in further why you think so? Can you further explain? Just like you are correct, just explain for the sake of simplicity.
Because curvature is A is
Yeah. So
curvature in
essentially,
A
yeah,
is bigger.
yeah. So essentially, the curvature for the C is greater than for B, which is greater than for A, and as we said that it is inversely proportional. So M star in C is actually which has the maximum curvature, so has the minimum. Just a moment. Has the minimum effective mass, and m star B, which is has the greater than m star C but less than m star A, which has the maximum because owing to its lesser curvature. Okay, so I think this is quite clear. Let us go to the second point, which was again very important, in which professor actually introduced the concept of extrinsic semiconductors. So intrinsic semiconductors are those conductors which has no doping. So when we apply doping, so So we add external impurities, we call it as extrinsic semiconductor, and the pure semiconductor which without doping, that is undoped, is nothing but the intrinsic semiconductor. So we saw that doping is actually a mechanism to control the density of carriers, that is the charge carriers, which are electrons and holes in case of semiconductors. So we can alter the properties of the bare semiconductor, which is intrinsic semiconductor, by applying or by adding different impurities. There are different types of impurities, like class 3 or group 3 or group 5 elements we can add in order to make a n-type and a p-type semiconductor. So there is also one fact that the carrier density is actually a temperature dependent. So if you just look at this particular picture, this particular graph, which tells you that the carrier density is actually a function of temperature, and it shows a very peculiar characteristic. So for this region, let's say at close to 0 Kelvin, you can say close to 0 Kelvin, there are no carriers. I mean, there is no ionization has been occurred. So there are no carriers, which means there are no carriers inside the conduction band. If you increase the temperature further up to say roughly about 100 Kelvin, so number of carriers increases in the CB because of the ionization happening inside the doped atoms, and we get partial ionization up to say 100 or 110 Kelvin. This is also dependent on a different particular semiconductor. So this is partial ionization. What if we further increase the temperature? So once we reach this particular point, we can say that all the donor atoms are fully ionized, and even if we increase the temperature, the uh, number of donors from the semiconductor, no donors from the donor atoms are not going to be increased. Only factor which is increasing is the intrinsic concentration, but we also saw that the intrinsic concentration doesn't vary much with doesn't vary like very significantly with this increasing temperature. So till this particular point, the carrier density actually remains almost constant. Ideally it we can say that it very slowly increases, but effectively you can say that it remains constant, and this region is also actually called as the extrinsic regime or extrinsic region. Now a point arises when we further increase the temperature, will actually gives more intrinsic carriers, and this particular region dominates, uh, and we can call it as intrinsic regime. So this is a peculiar nature for the temperature dependence of carrier density in a typical extrinsic semiconductor. Now if we go to the next point, we also saw a function called as the Fermi function. So in when dealing with the semiconductors, we deal with higher numbers of electrons, and which are our charge carriers, also holes. So these are statistically quite huge numbers, so we need statistical treatment, and for that we use a particular function called as Fermi function, which gives us the distribution of our charge carriers inside our semiconductor at particular energies. So f of e actually gives the probabilities of finding our charge carriers at different energies. So this is the function. If we try to plot it at let's say at different temperatures, so let me just draw a simple diagram to tell you. This is the Fermi function, which is of function energy E. Now let's say let's take this point in energy as EFF. Okay, so let's say at temperature is equal to 0 Kelvin or 0, and a condition is that our E is less than E of F. So we'll have, when E is less than E of F, we'll have exponential of this particular quantity uh, going to be 0. So F of E actually is equal to 1. So for E less than EF, so essentially this condition, for E less than EF, we have Fermi function actually equal to 1. Now let's take the condition for E greater than EF. In that case, our Fermi function is actually 0 because exponential becomes infinity. So if you take our 0 here, when E is greater than EF, we have this particular form. And another important case is when E is actually equal to EF, and for that case we get F of E is equal to 1 over 1 plus 1, that is F of E is equal to half. Okay, just a moment. Okay, so this is all about this is actually at temperature T is equal to 0 Kelvin. But when we increase the temperature, this particular curve becomes somewhat like this. So the F of E is actually stretching the Fermi level, and we can also, from this particular relation, we can also define our Fermi energy, that is EF. So EF is equal to, EF is actually the energy where the Fermi function is given as 0.5 and it is independent of temperature. So as we increase the temperature, when temperature is increased beyond 0, we see that the Fermi function actually stretches around EF. Another point was that the Fermi level is at the middle of the band gap when we are considering the intrinsic semiconductor, and it varies with respect to the doping. So if we just try to plot, let's consider this is our conduction band energy, this is our valence band energy, and this is our Fermi energy for the intrinsic semiconductor. So we have our so we have our Fermi function given as this particular form, and when we actually add the dopants into it, so let's say if we add the ND, that is number of dopants inside our intrinsic semiconductor, this Fermi function, so it is not symmetric actually here. Let's say this is 0.5. So when we add our Fermi our dopant, it increases the value of Fermi level. So our new Fermi level becomes this, and so we can say that it is increased. And similarly, if we add the acceptor impurities, so when we add the acceptor impurities, the Fermi level goes towards the valence band energy. So we can say that the Fermi level varies with respect to the doping and also with respect to the concentration of the doping. Going to the last slide for the review just. So Fermi level is also dependent on the doping density. So as we saw in the last slide, as we increase the concentration of doping, say when we increase the donor concentration, so donor concentration is increased in this region. As we go on increasing, we see that Fermi level tries to go towards the conduction band, and it saturates at particular point. There is a special case that we cannot cross because of the degenerate semiconductors and so on. We won't go into the details. Similarly, for the p-type semiconductor, in which if you increase the number of holes, that is number of acceptor concentration, the Fermi level tries to reach towards the valence band energy, in which N is increased in this region. Also, there is impact of temperature on the Fermi level. So as we saw in the temperature versus concentration gap graph, there is a characteristic peculiar curve for the carrier density with respect to temperature, and if we further increase our temperature, we go into the intrinsic region. So this is intrinsic region, and as we increase the temperature further, the Fermi level, as we know, inside the intrinsic semiconductor, tries to become EFI, which is at the middle of the band gap. Okay, so yes, I think this is all about the review, and yes, so all that I discussed is summarized just for completeness. So effective mass is given by this particular formula, in which m star, as you can see here, is inversely proportional to the double derivative of energy with respect to the k, that is our wave vector. And next is the equilibrium carrier concentrations. The carrier concentrations for intrinsic semiconductors are shown here, in which N0 and P0 are the thermal equilibrium electron and hole concentrations respectively, which are given by Nc exponential minus EC minus of EC minus EF by KT, in which EC is the EC is the conduction level energy of conduction level. Then EF is basically our Fermi level, and yes, so the intrinsic carrier concentration is also given by this particular relation, in which Ni square is given as Nc Nv times exponential of minus Eg by Kt, where Eg is the band gap. And K is our Boltzmann constant, and T is temperature in the Kelvin. Also, if we go to the last point, the equilibrium carrier concentrations in the extrinsic semiconductor case is also given. So EFI is the Fermi level for the intrinsic semiconductor, and EF is this Fermi level when there is doping is present inside our semiconductor. So N0 and P0 are the thermal equilibrium electron and hole concentrations respectively. One more important relation, also called as the mass action law, is given here, in which N0 P0 is equal to Ni square. And you need to remember these relations. These relations I have deliberately summarized here because we will be solving problems based on these relations. So I think this actually forms a brief summary. You can find this particular summary in the course page as well. So I have just written here just for the sake of completeness. I think we would just like to start with the questions now. So I'll solve 8 questions which are from the previous year's offerings, as well as a couple of gate questions also I have added. Can you just confirm you could hear me well and see my screen well?
Yes, sir.
Okay, thank you. So let's start with the question number 1. Let me just take a pen here. Okay, so the first question is as follows. A simplified E versus K curve is given. This is for an electron in the conduction band. The value of A is given, which is 10 angstrom, and we are asked to find the relative effective mass. So the relative effective mass is essentially the effective mass divided by the actual mass or the rest mass of electron. And one hint is also given that you can use E minus EC value for k is equal to pi by a to compute first of all the C1. So we have given here the value of E which is equal to EC plus 0.32 electron volt, which is at pi by a. So we can simply write E minus EC which is equal to 0.32 electron volt. Remember, it is at k is equal to pi by a. Now we need to find the m star over m naught. So we know the one relationship, that is 1 over h cross square d2e over dk square is actually given by 1 over m star, which is equal to twice c1 times h cross square. So our first indeed are just, you can see from this particular relation we have used it here. So we'll directly use this particular formula to calculate m star first. So let us say okay, so 0.32 electron volt, that is 1.6 into 10 to the power minus 19 times joule. Yes, so we also know one more formula in which E minus EC is given as C1 times K1 C1 times K square. Okay, so applying it here, I'm sorry, this is wrong. We need to set it is equal to C1 times K is, in our case, is pi times A, so pi by A square. So we can find value of C1 from this particular relation. So we'll have C1 which is actually equal to 5.19 times 10 to the power minus 39. So now we can use this particular value of C1 and find m star from this relation. So just writing m star over m naught, which is our relative effective mass, which is equal to h cross square over twice C1 times m naught. So if you just substitute value of h cross, which is 1.05 times 10 to the power minus 34 whole square divided by 2 times C1 is 5.19 into 10 to the power minus 39 times the rest mass of electron. We are considering electron here, so it is 9.1 into 10 to the power minus 31 kilogram. So if you just calculate this particular thing, you will just get the value of m star over m naught, which is equal to 1.17. So the relative effective mass m star by m naught is actually 1.175. Okay. Okay, so let's move to question number 2. Okay, so the question number 2 is as following. It says that calculate the probability that quantum state in the conduction band at E is equal to EC plus KT by 2 is occupied by an electron, and calculate the thermal equilibrium electron concentration in silicon at T is equal to 300 Kelvin. We can just picturize this particular as follows. This is our conduction band, and our actual energy level, which is here, this difference is actually KT by 2, and calculate the thermal equilibrium. Okay, assume the Fermi energy is 0.25 electron volt below the conduction band. So our EF is below our conduction band, and that value is 0.25 electron volt. Okay, the value of NC is also given. Okay, so we can just basically write the formula. The probability that quantum state at E is equal to EC plus KT by 2 is occupied is actually given by our Fermi function that I mentioned in the previous slides. So f of E is actually given as 1 over 1 plus exponential of E minus EF by KT. So we can approximate this particular relation to just give us the exponential of E minus EF by KT. RE is given as EC plus KT by 2 minus EF divided by KT. Okay, so from this we can say that also we from this particular diagram you can say that EC minus EF is 0.25. So it turns out that exponential of minus of EC minus EF is actually 0.25 plus KT by 2. So it is 0.25 plus KT is actually 0.0259. So you can calculate KT. I'll show you in the next couple of minutes. So KT is given by 1.38 into 10 to the power minus 23. Okay, times the temperature is 300 Kelvin, but we want in the say electron volt unit, so we divide it by 1.6 into 10 to the power minus 19. This value comes out to be 0.0259. So f of E is actually comes out to be 3.9 times 10 to the power minus 5. So you can see from you can just try to see here that the probability of an electron being found at this particular energy, which is above a conduction band by KT by 12 KT by 2, is 3.9 times 10 to the power minus 5. This value seems to be a very small value, very less as compared to value of unity. So let's first then calculate the concentration also. So calculate the thermal equilibrium electron concentration. So we know we have a relationship for that. So N0 is given by Nc times exponential of minus Ec by Ef by Kt. So if you just substitute the value of Nc, which is 2.8 times 10 to the power 19 Cc, and exponential of Rec minus Ef is Kt by 2, which comes out to be 0. No, this difference Ec minus Ef is actually 0.25 electron volt, and the KT, as I told you, is 0.0259. Therefore the equilibrium concentration, electron concentration at T is equal to 300 Kelvin, comes out to be 1.8 times 10 to the power 15 per centimeter cube. So one comment I would like to make here is that the probability of a state being occupied can be quite small. So if you can see here, it is very less than 1. But the fact that there are a large number of states, there are so many statistically huge number of states, which means that the electron concentration is actually a reasonable value here. So despite being such a low probability, the concentration of electron density is a considerable number. Okay, so let's I hope it is clear. Let's move to question number 3. Question number 3 is as following. This is a conceptual question. It is as follows. It says, just a moment, let me check if recording is going on. Yes. Okay, so as temperature increases from T is equal to 5 Kelvin to T is equal to 700 Kelvin, the carrier concentration goes through 3 regions, and in what order does the transition occur? So actually we have discussed it quite in detail, so but still can anyone just give the obvious answer? I would like to hear.
Partially ionized intrinsic extrinsic.
I'm sorry, could you speak a little louder?
Partially ionized in extrinsic intrinsic.
Yeah, yes. So as we mentioned, it goes from the partial ionized states to in extrinsic state to an intrinsic region. Okay, so let's move on to our question number 4. The question number 4 is I have taken from a previous year's GATE exam question. So it was in GATE Physics 2016. So the question is as follows. The energy versus wave vector relation, that is our EK relation, is given. It is given by A times Ka square plus B times Ka to the power 4, and the lattice constant is also given as 2.1 angstrom. The values of A and B are given. At the bottom of the conduction band, the ratio of the effective mass of the electron to the mass of the free electron is. So what we have asked is the relative effective mass, as we calculated in our first or second example. Okay, so E as a function of wave vector is given here. So A times K2 square plus B times Ka to the power 4. So let us take a first derivative of this particular relation. So dE by dk will give us twice A K A plus 4 times B A cube A to the power 4. Let us take the second derivative of this particular equation. We'll have d2E by dk square, which is equal to twice A times A plus 12B K square times A to the power 4. Now we know that our effective mass m star is given as 1 over h cross square d2E by dk square. So just substitute this particular value, substitute this particular relation in this particular equation. We'll have also the condition is given that the bottom of the conduction band. So at the bottom of the conduction band, we know that the value of K is equal to 0. So we can write for the m star over m naught, which is our relative effective mass, which is essentially equal to h cross square by d2E by dk square times m naught. So just substituting the value of h cross, which is 1.05 times 10 to the power minus 34 whole square divided by d2E by dk square. So when we put the value of k is equal to 0, this particular thing goes to 0. So d2E by dk square is essentially just 2a times e, 2a times capital A times small a. So it is essentially 2 times, it is given as 6.3 into 10 to the power minus 19, our A is 2.1 angstrom. So well, A square is here 2.1 square into 10 to the power minus 10 square, that is 10 to the power minus 20, times m naught. M naught is again the mass for the free electron, which is 9.1 into 10 to the power minus 31. So if you just calculate this particular equation here, we'll get the value of m star over m naught, which is our the effective relative effective mass of electron, and it comes out to be 0.22. Okay, is it clear?
Yes, sir.
Okay, so let's move on to another small conceptual problem. It is quite an interesting question. So what it tells you is as following: assume that the Fermi level is near the valence band, and which of the following is true. So uh, four relations are shown here, and we are asked to actually show which of the following is correct, given the fact that the Fermi level is near the valence band. So can uh, can anyone just guess from this particular information that our Fermi level is near the valence band? So what can be the relationship between these three parameters? I will explain it, but if you can tell,
Option
that would
3.
be great. Yeah, tell me.
Option 3.
Just a moment, I'm not able to hear you. Okay,
C.
option
Option
3.
C.
option C. Okay, let us discuss it. Okay, so let us take this in terms of the diagram. So what it is telling us is that if it is our conduction band, if this is say our Fermi level at the intrinsic semiconductor for the intrinsic semiconductor, and if this is our valence band energy level, what it is telling is our Fermi level is near the valence band. So our Fermi level lies somewhere in between these region. So we can say our Fermi level is here. Okay. Now the fact that Fermi level is near our valence band, it is essentially telling us that this is our p-type semiconductor. Okay. Okay, so once it is established that it is a p-type semiconductor, we know that in a p-type semiconductor, the majority carriers are holes. So p has to be greater than n. So the option is C option here, and also we need the value of p to be more than the number of the acceptors to be more than the intrinsic carrier concentration, so that we'll have a extrinsic semiconductor, because when the intrinsic carrier concentration is more, the Fermi level will be shifted towards the intrinsic Fermi level. So okay, if you can consider other options as well, like n is equal to p is equal to ni, which tells us effectively that it is a intrinsic semiconductor where the electron and hole concentration is same. Here it is telling us for the n-type semiconductor, because majority carriers here are the electrons. This is our correct example. And so let us go to the question number 6. Okay, so this is also quite an interesting problem. Okay, let me read it for you first. A company X aims to design a new semiconductor material. The semiconductor is to be a p-type. So a semiconductor is to be a p-type, and it is doped with Na. The concentration is given as 5 into 10 to the power 15 per centimeter cube acceptor atoms. Assume the complete ionization and Nd is equal to 0. So this is also an important condition. The effective density of states function, that is Nc, is given, and NV is also given at T is equal to 300 Kelvin, and it varies as T square. So this is also an important piece of information that we'll need. A special semiconductor device fabricated with this material requires that the hole concentration be no greater than 5.08 times 10 to the power 15. So we are given the hole concentration. So P0 is given, and it is given at 350 Kelvin. The minimum band gap energy required in this material is, and we are supposed to calculate Eg. Okay, so we know a relation that Ni is equal to under root Nc times Nv exponential of minus Eg by 2 kT. So we need to find the band gap. So essentially from this relation we can see that we need the value of information of Ni, Nc and Nv. So we need three different parameters to find out the value of band gap, that is Eg, and these values we need at 350 Kelvin. These values are given at 300 Kelvin. We need to find them first at 350 Kelvin, and then we can substitute them in this particular formula and we'll get the value of Eg. Okay, so let us first calculate the value of Nc at 350 Kelvin. One piece of information given here is that it varies as T square. So Nc at 350 Kelvin is essentially Nc at 300 Kelvin times 350 by 300 whole square. So Nc at 300 Kelvin is 1.2 times 10 to the power 19, and if you multiply by this, we'll get Nc at 350 Kelvin to be 1.63 times 10 to the power minus plus 19 cc. Okay. Similarly, we can find out the value of Nv at 350 Kelvin, which is equal to Nv at 300 Kelvin, that is 1.8 times 10 to the power 19, this value, times 350 over 300 whole square. So Nv at 350 Kelvin is again comes out to be 2.45 times 10 to the power 19 cc. Okay, so we have the values of Nc and value of Nc, value of Nv. Now we need to find the value of Ni at 350 Kelvin. So for that we can use a condition called as the charge neutrality equation. So the charge neutrality equation is actually a important condition. So when we have the thermally inside a thermal equilibrium, the semiconductor crystal is electrically neutral and the electrons are distributed among the various energy states, creating negative and positive charges. But the net charge density remains zero, and this charge neutrality condition is used to determine the thermal equilibrium electron and hole concentration as a function of impurity doping concentrations. So the charge neutrality conditions is expressed by equating the density of negative charges to the density of positive charges. So we then have the charge neutrality condition as the charge neutrality condition as P0 plus Nd is equal to N0 plus Na. Here shown is that Nd is going to be 0, and also we know that N0 is equal to Ni square by P0, because N0 P0 is equal to Ni square is our mass action law. So from this we can substitute this particular relation here, and we can find from the values of Na and P0 the value of Ni, which Ni square we can actually find, and it comes out to be 4.06 times 10 to the power 29. Okay, so we have Ni square, we have Nc, we have Nv. So let us put this in this particular equation and we'll find the value of Eg. So Ni square is equal to Nc times Nv with exponential of minus minus Eg by Kt. So if you can just substitute all these values of Ni, Nc and Nv, uh, we can solve for Eg. So we can take logarithm on both sides and we'll end up with Eg, which is equal to around 0.625 electron volt. So I have skipped couple of steps here, but these are elementary steps. I think you can follow them. So Eg is 0.625. Okay, so now let us move to a couple of last questions, of which the question number 7 is as follows. Two semiconductor materials have exactly the same properties, except material A has a band gap energy of 0.90 electron volt and material B has a band gap energy of 1.1 electron volt. The ratio of intrinsic concentration Nib of material B to that of intrinsic concentration of Nia of material A at temperature 400 Kelvin is. So we need to find the ratio of intrinsic concentrations at 400 Kelvin. So again we know the formula that Ni is essentially equal to under root Nc times Nv with exponential of minus Eg by 2 Kt. So it says that the same properties except band gap. So we can just simply write the ratio here Nib over Nia is equal to exponential of minus Eg's are 1.1 for B by twice Kt divided by exponential of 0.90 over twice Kt. Okay, so let us first find out value of Kt at 400 Kelvin, which is 1.38 times 10 to the power minus 23 times 400, and we want it in electron volts. So 1.6 into 10 to the power minus 19 we can divide, and Kt at 400 Kelvin is essentially 0.0345. Okay, so this ratio actually becomes exponential of minus 0.2 divided by twice Kt. So we can put the value of Kt from this particular equation and we'll get 2 times 0.345. Therefore the ratio of the concentrations for B with respect to A is actually comes out to be 0.055. Okay, followed everyone?
Yes, sir.
Okay, so we'll move towards our last problem, last question for this particular session, and it is again a conceptual question. I have taken it from the GATE question paper for physics in 2013. So the question is as follows. A phosphorus doped silicon semiconductor, the doping density is given 10 to the power 17 per centimeter cube. Just a minute. Given, and we are asked to okay, so it is heated from 100 degree centigrade to 200 degree centigrade, which one of the following statements is correct? This is the question. So the phosphorus doped semiconductor is there, and we saw from this particular relation here that when we increase the temperature of our extrinsic semiconductor, it moves from its value at the extrinsic level to towards the middle of the band gap, because it essentially reaches the intrinsic region. So the answer for this is quite obvious, but a little tricky question as well. So can you just tell me which one of these four options is correct?
Position of Fermi level moves towards conduction band.
No, it doesn't move towards the conduction band. It actually moves towards the middle of energy gap. So as I told you that in the peculiar form in which the concentration versus temperature is given, which follows this particular form. So when we increase the temperature from 100 to 200 degrees centigrade, the extrinsic semiconductor essentially becomes the intrinsic semiconductor, which reaches the intrinsic region. And in the intrinsic region, we know that the Fermi level is given as EFI, which is actually at the middle of the band gap. So therefore, the position of Fermi level moves towards the middle of the band gap. So here you can see the position of the Fermi level when we increase the temperature moves towards the middle of the band gap, which is at the intrinsic level. So it depends upon different concentrations, but taking a simple concentration, one concentration, you can see for 100 to 200 or different temperatures, it tries to move towards the middle of the band gap. Okay, so is it clear?
Yes, sir.
Okay, so I think
Sir?
yeah, tell me.
And if we increase more temperature, then it will come towards valence band.
No, why would it come towards valence band? It will try to go towards it will try to reach the intrinsic level, so which essentially marks the intrinsic region. So it will not go towards the valence band. It will try to go close to the intrinsic level, but it will not come down to the valence band.
Okay, thank you.
Okay, so with this, I would like to thank you all for joining for this particular session, and we will meet on the 12th August, Friday 12th August at 6 p.m. for our next session. So as I have told you a number of times that this is the NPTEL course link where you can go and find different resources. The recorded sessions, recorded live sessions will be uploaded onto a dedicated YouTube channel, so you can find these recordings there. In case you are not clear about some concept or anything, you can ask questions in the discussion forums at the NPTEL course link. You can check out the recordings again if you are not if you did not follow anything in the live session, or if you could not join due to any reason. So you can find these recordings in the YouTube channel, and also you can find the discussion session on discussion forum in the NPTEL course link. So you can take benefit of these different resources. So any questions, any comments, or if not, we will close the session. Anything you would like to say, or any comment? Okay, so there is quite a silence here.
Thank you, sir.
Thank you. Okay, thank you so much again, everyone, for joining for this second live session for the course, Introduction to Semiconductor Devices. I hope to see you all in the third live session, which is scheduled on the 12th August at 6 p.m. Indian Standard Time. Till then, bye bye, take care, and have a nice weekend.